I want you to imagine a system of waterfalls. Maybe these are pipes or channels of some kind that water can flow through. And the water starts out at some certain height and flows downward, falls at the first waterfall, falls at the second waterfall, falls at the third waterfall, and so on until it gets to the end. And then the water flows back to the starting place. And then some kind of pump lifts the water back up to where it started. Just for fun, let's call this pump epsilon. And let's call each of the waterfalls R1, R2, and R3. Now the key here is to note that each of the waterfalls is dissipating gravitational potential energy for the water. So the water falls and it loses gravitational potential energy. And then once we get back to the end, the pump right here, the pump is putting gravitational potential energy back into the system. Now let's take a look at a DC circuit with 3 resistors. And the resistors are conveniently labeled just like our waterfalls from before, R1, R2, and R3. And then there's a battery epsilon that's putting all of the potential energy into the system. So the very same sort of thing is happening. Each of these resistors dissipates energy, and the battery is putting potential energy back in. Take a moment to thoroughly convince yourself that these two systems really are analogous to each other. Each of these waterfalls dissipates gravitational potential energy, while each of the resistors dissipates electrical potential in some way. And then the pump lifts the water level back up to where it started in the same way that the battery puts that potential back into the circuit. Now notice that the sum of each of the heights of these waterfalls has to equal the total height that the water started from. In other words, if I look at the height that the pump raises the water to, and then add to that the drop across each of the waterfalls, the sum has to be 0 because the water ends up here at ground level in both cases. Now, the very same thing is true, although in a more abstract sense, for the circuit. And that leads us to Kirchhoff's loop rule. Kirchhoff's loop rule says that for any closed loop inside a circuit, the sum of all of the voltages has to add up to 0. This Greek letter sigma just means that we're adding up all the voltages, all the voltage changes. And since, remember, voltage is really a measure of electrical potential, we're saying the same thing as we did here in the waterfall system, that the sum of all the changes in height has to equal 0, height corresponding to gravitational potential energy. Kirchhoff's second rule has to do with something called junctions. First of all, let's think about what a junction is. Here's a simple resistive DC circuit. Let's label a couple of points to look at. Let's call that one P1 and P2. Is P1 a junction? Well, it looks like it might be because that's sort of an identifiable point within your circuit and the wire sort of comes to a point right there. But really, if we look at it more closely, that's just one piece of wire that's bent around. So that's one spot in a piece of wire. That's not really a junction. P2 is a proper junction because you have 3 wires coming together. 3 or more wires coming together, that's a very interesting place to look at. This is not really a junction, although Kirchhoff's junction rule does actually work here. It's only trivially true. But a place where 3 or more wires come together, that's where we really need to apply Kirchhoff's junction rule. So let's look at a junction more closely. We can label a separate current on each of the 3 branches of this junction. Let's call this one I1, this one I2, and this one I3. First, a note about convention. Any current that's going into the junction we're going to label with a positive sign, and any current leaving the junction we're going to label with a negative sign. Now we're going to present Kirchhoff's junction rule in an argument by contradiction. Now we know that what actually makes a current happen in the wire is the flow of electrons along that wire. Now for historical reasons, the conventional current goes against the flow of electrons, so we're going to imagine a flow of positive particles instead, so that we can draw them in the same direction as our currents. But just know that in fact these are electrons moving in the opposite direction. We're just going to imagine it in this way for the sake of argument. Now with all these charges from I1 coming into the junction, If fewer charges left this junction per unit time, then there would be charge piling up right here at this junction. That is to say, if I3 plus I2 was not as big as I1, you'd have a whole bunch of charges piling up right here. We know this can't happen because positive charges don't like to hang out near each other, so this is going to create a massive potential to go ahead and push these charges along the wire. Now imagine that instead, I2 and I3 are both much bigger than I1, or the sum of them together is. Then you're going to have more positive charges leaving this junction than there are positive charges coming in, and you're going to have a partial negative charge building up at the junction, and that's going to cause the same thing in reverse. So you can't really have charges piling up along the wire like this. So what this means is that all the current entering the junction, which in this case is just I1, has to be equal to the sum of all the currents leaving the junction, which in this case is I3 plus I2. Or notice that if I just add all the things on the same side and properly account for the sign that I put in for each one, then those things have to add up to 0. That's just a statement of Kirchhoff's junction rule. Generally speaking, if we have any number of currents that we like, not just the 3, Kirchhoff's junction rule says the sum of all the currents at a junction is equal to 0. So in summary, we have 2 rules. Kirchhoff's loop rule says that the sum of all of the voltages inside a closed loop in a circuit has to add up to 0. And Kirchhoff's junction rule, which applies only at a junction, is that the sum of currents at that junction has to equal 0. It's really important to note that voltage goes with loop and that current goes with junction. It seems like it's really self-evident from the statement of these rules, the loop rule and the junction rule, but it's actually a bit harder to remember than you might imagine because the form of these rules is both the same, that you have the sum of something at somewhere adding up to 0. So the more problems that you solve with these, the easier they'll be to remember. One final note is that sometime you will see these written as Kirchhoff's laws. I prefer not to think of them as laws because they actually are just observations based on other laws. Like Kirchhoff's loop rule, for example, is simply an application of the conservation of energy, and it's not really its own new law. But it really doesn't make a difference. I tend to say rule, and then you'll see them written as law in some other places, and they mean the exact same thing. So the project in Lab 5 is to build DC circuits, DC resistive circuits, and actually test out Kirchhoff's rules. So in our first slide, we see a statement of Kirchhoff's loop rule for a circuit with 3 resistors like I drew just a moment ago. Here they have the battery written as delta V instead of epsilon like I had it. That doesn't make any difference. And then also notice that for each of the voltage drops across the resistors, they've gone ahead and written minus IR1, minus IR2, and minus IR3. So let's think about the reason for that. Across each of these resistors, Ohm's law still applies, right? So the voltage drop across there has to have the form IR, so IR1, IR2, and IR3. And since resistors dissipate energy instead of adding energy into a circuit, or potential, rather, they dissipate potential instead of adding potential back into the circuit, we have these minus signs associated with each one. This does in fact align with our intuition that the battery is positive, so the voltage drops across the resistors have to be negative in order for the whole sum to be 0. Here's a note about something we call the voltage divider rule, which is really just a way of finding a voltage drop across one of the resistors in terms of nothing but the resistances and the total voltage of the circuit from the battery. You can work this out for yourself just by noticing that the current has to be the same for each of the 3 resistors because it's in series, and then just a bit of algebra. So, for example, I is V over R by Ohm's law, so that means that V1 over R1 equals I, V2 over R2 equals I, and then the total delta V over R1 plus R2, which of course is the equivalent resistance, is also equal to I. All 3 of these have to be the same current since the thing is in series. So since they are all the same current, you can equate this expression with this one, and you get the voltage divider rule for delta V1, we solve for that. And then likewise, if you equate the expression with delta V2 in it with the one for the total voltage. Here's the slide for Kirchhoff's junction rule, and it basically just introduces the rule in much the same way as I did before. Junctions are sometimes called nodes, so if you hear that term go by, that's what that means. And then, again, just keep in mind that the sign of the current reading is to indicate the direction of the current. That means into the node is positive and away from the node is negative. We find the current divider rule in much the same way as we found the voltage divider rule. Of course, on a parallel branch, we don't have equal currents anymore, but instead we have equal voltages. And so by equating voltages, we can find very analogous results to what we found before. And also notice that intuitively what this means is that of these two branches, the one with the greatest resistance is going to get less of the current. So if you can imagine this as, instead of electrical current, but like water, for example, if water is being split into two hoses and you squeeze one of the hoses really tight, more water is going to go through the other hose. Now, of course, we're not actually doing this experiment at the lab, but I do want to include a couple of notes, as though we were. So this thing is a multimeter. It measures things like currents, resistances, and voltages, and so forth, for basically measuring all the stuff that you might be interested in if you're examining a circuit. So if you're measuring a voltage, you can kind of imagine red should be the positive side and black should be the negative side. And so if the current is going from red to black, you're going to get a positive reading. And if the current is going from black to red, you're going to get a negative reading. In order to confirm Kirchhoff's loop rule, you would need to measure the voltages across each of those resistors all the way around a loop, like we have pictured here. So it's obviously imperative that we keep those signs straight, or else they won't add up to 0, like they should. And so it doesn't matter which convention you choose, red before black or black before red, but you would need to keep those in the same order all the way around the loop. In order to properly measure the current at a junction, keep the black probe on the junction all the time, and then move the red probe onto whatever branch that you're interested in. So let's say, for example, that you have your ammeter connected up like this, and you get a positive reading on your ammeter. That means that the current is moving toward the node from this branch right here. Or, for example, connected to this branch and you get a negative reading, that means the current is going away on that branch. And as long as you keep the black probe on the node all the time, then it will always give you the proper reading with the signs, and then when you add all those currents up, you should get something very, very close to 0. I think that should be all the information you need to go ahead and complete the lab. So I hope you found this video helpful, and as always, if you have any more questions, feel free to contact me or any of the other TAs.